Alright guys, good afternoon. Today we're going to be covering Unit 13 review in our online continued learning section of the course. This is the review that will be very similar to the Unit 13 test, which will be up on Schoology tomorrow. Make sure that you guys are ready to take this test, review the notes, review the videos, review homeworks. Make sure that you guys understand what's going on with these. If you guys have questions, make sure that you ask me. This review will be your best tool to study for this. If you don't use this review, the test will be much more difficult. If you guys have questions, please be sure to let me know before you test. If you let me know anytime that the test is open, I will not answer those questions. Only ask questions before the test date is open. It will be open tomorrow morning. I'm going to open it at 9. It'll be open until, I'll probably have it open until midnight. Just make sure that you guys do attempt it. You're going to get one shot at it. And if you guys have questions, you got to let me know before 9 a.m. Anytime after that, I won't be answering any questions on it because it will be a testing period. Other than that, be sure to read all directions on the test and be super precise with your answers. If you're not super precise, you will miss points. There will be a time limit on this test of an hour, just like any class period that we'd normally have during the school day. So you guys will have 59 minutes or 60 minutes to complete this test. Just make sure that you guys are getting it taken care of within that time limit. Anytime after that, the test will stop, and you'll get whatever score that you scored on with it. So just keep that in mind. All right, so without further ado, let's go ahead and get into our review. So, number 1, circle the exponential growth equation, underline the exponential decay equation. So if we look at this, we have these two equations here. Y equals negative 2.5 times 0.04 raised to the power of x, and y is equal to negative 2.5 times 4 raised to the power of x. So if we recall, these are all written in the form y is equal to a times b raised to the power of x, where a is our initial value, b is our growth or decay factor, depending on whether it's bigger than 1 or less than 1, and x is our input value. It's our variable that we plug numbers into. So, for growth, we know that we have growth in an equation if our b value is bigger than 1. That means that we have growth, if b is bigger than 1. If our b value is less than 1, then it's decay. So as we look at these, y equals 0.25 times 0.04 raised to the power of x. Well, this 0.04, that is our b value. And we see that our b value is less than 1 there. So, in fact, this first equation, that would be decay, so I'm going to underline it. Meanwhile, for our other equation here, y equals negative 2.5 times 4 raised to the power of x, well, we see our b value is 4. So this would, in fact, be our growth equation, and that's why we're circling that one. So keep that in mind. If our b value is less than 1, it's decay. If our b value is greater than 1, it is growth. All right. Pretty straightforward. Moving on. Number 2, find the growth or decay factor, or the b value, of the following functions. So again, we're just looking for our b value here. We don't need to do any math for this one because it's already set up in the form where we have b. So we are just looking for the b value. This is not asking for growth or decay. I don't care whether it's growth or decay for this. I just want the b value. And if you're not very precise on the test with these, you will mess up your answers. So please be careful. So looking at this, for our first one, our b value, once again, is whatever is raised to the power of x. So that 0.04, that is our b value. Meanwhile, for our second one, the number that's raised to the power of x is 4. That would be our b value in that case. So we can easily tell these based upon which is our b value, which number is being raised to the power of x. Again, it's whatever number's inside the parentheses here. All right. Find the percent rate of change r of the following functions. Now, this one's a little bit more difficult than the previous ones. The r value is much more difficult than what we've covered in the past as well. If you guys recall, b is equal to 1 plus or minus r. So the 1 plus or minus r is what typically goes inside these parentheses here. Now, if it's growth, we use plus. If it's a decay function, we use minus. If we look at letter A here, f of x is equal to negative 2.5 times 0.04 raised to the power of x. Our b value is 0.04, which means that this is actually a decay function. as we know. Our b value is less than 1, so we must have decay. So therefore, I can plug that into this equation right over here. B is equal to 1 plus or minus r. And I can solve for r for this. So let's go ahead and do that. We get 0.04, which is our b value, is equal to 1. Now again, this is a decay function, so we're going to use the minus here. So 1 minus r. Now from here, we go ahead and we solve for r. Oops, sorry. We go ahead and we solve for r. Again, we have b is equal to 1 minus r. 0.04 is equal to 1 minus r. I subtract 1 from both sides. Now this will have the 1's cancel out on the right side of our equation. On the left side, we're left with negative 0.96 equals negative r. Now, r is not by itself quite yet. It has this negative attached to it. So to get rid of a negative, I divide both sides by negative 1, or multiply both sides by negative 1, your call. The negatives cancel each other out, and we're just left with r is equal to 0.96. Lastly, we can't forget that this is a percent rate of change, so this needs to be written as a percent. So I take my decimal place and I move it 2 places to the right, giving us 96% equals r. And again, this is a growth function here. This is growth. So we want to make sure that we know that it's growing. Or sorry, this is decay. I misspoke. This is decay, so we want to make sure that we know that this is a decay function, a 96% decay of our value. On to letter B. F of x is equal to negative 2.5 times 1.75 raised to the power of x. Now in this case, our b value is 1.75, which means that this must be growth occurring. So if this is growth, again, we can do the same exact process. B is equal to 1, and then this time, since it is growth, it's going to be plus r. From here, we know that our b value is 1.75 is equal to 1 plus r. Then we just solve for r. We subtract 1 from both sides. This will leave us with r is equal to 0.75. Now from here, I move my decimal place 2 places to the right, leaving us with r is equal to 75%. In this case, we have growth. So again, these are the more difficult problems because we got to actually do a bit of math, and we got to remember that it's minus if it's decay, plus if we have growth. So from there, that's the hardest part of this entire section, I think. Number 3, figuring out what r is. Just remember, b is equal to 1 plus or minus r. And then use your common sense. We're adding if it's growth. We're subtracting if it's decay. And then here's just the work for it. Again, and at the end, I would prefer if you guys wrote growth or decay. Since this is an online test, you won't need to actually write that out. I'm just going to be looking for the percent. So make sure that you leave it as a percent, not as a decimal. If you leave it as a decimal, you're going to miss some points on it. So please keep that in mind. All right, number 4. A person invests $4,200 in the bank, and it grows at 3% per year. Write a function that represents the total value of the investment in each year, and then afterwards we'll find the value of the investment after 9 years. So looking at this, the information that they gave us, they said that we invested $4,200. So that's our initial value. That's how much we're putting into the bank to start off with. So that would be labeled as our A value. Meanwhile, it's growing. So that means that this would be, in fact, a growth function. And then this 3% here. We need to know whether this is our B value, our R value, or our X value. Now, since it's a percent, since we see percentage, that means that this is, in fact, an R value. So we need to switch that R value to B so we can plug it into our formula. So getting started, let's go ahead and work with that R value to get started. We have 3%. Now, if I want to switch this to a decimal, I take where that decimal place naturally is after the 3, and I move it 2 places to the left, giving us 0.03. That's what our R value is. Now we can't forget the formula B is equal to 1 plus or minus R. In this case, we have growth once again, so we're going to use the plus. So we have B is equal to 1 plus
plus r, well, r is 0.03, as we see right up here above it, giving us our b value as 1.03. Now from here we can go ahead and plug this in to a function. We want to create our function, so let's go ahead and do that. These functions that are exponential are written in the form f of x equals a times b raised to the power of x. Now we're just substituting in for the variables a and b. We don't need to substitute in for x right now, and this f of x is the same as y. So you can also write this as y is equal to a times b raised to the power of x. Most likely you'll see it written like this on the test, so keep that in mind. So let's go ahead and plug in our values. We have f of x is equal to a, which is 4,200, times b, which is 1.03, raised to the power of x. And there's our function. Again, this is the part that you guys will need to enter in on the test. I don't need the f of x or anything like that. So please keep that in mind. Letter B. Find the value of the investment after 9 years. Well, we got to think of what we'd plug 9 into. If we think back to the very, very start of the year when we were dealing with distance versus time graphs, we knew that distance was always our y-axis and time always deals with x. Now, at this point, let's think. It's years. Years is a measurement of time, so that means that we're going to plug 9 in for x. So let's go ahead and do just that. I plug in 9 for x, we have, and I'm just going to switch this to y to show that it doesn't matter if it's f of x or y. Y is equal to 4,200 times 1.03 raised to the power of 9. If we enter that into our calculator, 4,200 times 1.03 raised to the 9th power, we're going to be ending up with y is equal to 5,480.05. Now again, we're rounding to the nearest cent because this is a value of money. So we're going to round to the nearest cent to know how much money we're having come into our bank account after those 9 years. So in 9 years, we earned $1,280.05. All right, moving on. Number 5. And here's the work for number 4 once again. Again, we switch it over to from a percentage to a decimal to deal with that r value, and then we plug it in. F of x is equal to 4,200 times 1.03 raised to the power of x, and then after that, we just go ahead and plug 9 in, and we're left with $5,480.05. All right, number 5. The population of wild deer in Alaska started at 2,220,000 and decreases by 20% per year. Write a function that represents the deer population each year. That's letter A. And letter B, how many deer will there be in 30 years? 40 years. How many years will it take for the deer to be considered extremely endangered at 700 or fewer deer? So looking at this, what we have currently with our setup, because again, we want to focus on A, and then we can try out B. So with A, we just want our function, so these will be written in the form A times our B value raised to the power of x. Now this 20% here, this looks very similar to the last problem that we did, number 4, where it gives us a percentage. Now think about what variable that would be. Would that be a B value? Would that be an R value? In this case, this would be an R value because it has a percent. And meanwhile, that 2,220,000, that's our A value. That's our initial population of deer. So let's go ahead and try this out. First thing that we do, we write our equation in the form f of x is equal to A times B raised to the power of x, where that 2,220,000 is our A value. And then we need to switch that 20% from R to B. So we have B is equal to 1 minus R this time. Now the reason that we're subtracting is because, again, we are decreasing this time through. So it's going to be a decay function instead. So again, this is going to be decay. From here, Well, I want to write this 20% as a decimal, so if I have 20%, I move my decimal place 2 places to the left, giving us r is 0.2. So we have b is equal to 1 minus 0.2, and you can have the 0 there if you'd really like to, which gives us b is equal to 0.8, or 80%. So again, this is where this middle section comes in. This is b is equal to 1 minus r. Again, I'm just plugging that 1 minus r in for b. I'm just substituting it in. From here, we can write out our function. F of x is equal to a, 2,220,000, as we talked about earlier, our starting amount, times b, 0.80, that's what we found over here, raised to the power of x. All right, letter B. How many deer will there be in 30 years? Oh, well, I just plug in 30 for x. In 40 years, well, I just plug 40 in for x. I solve for y. And then how many years will it take for the deers to be considered extremely endangered at 700 or fewer deer? Now, for this section, I highly suggest that you use the table function on your calculator. If you recall the table function on your calculator, it'll be extremely useful for you guys to use. If that doesn't work, just do a guess and check. So if you realize, hey, after 40 years, it's still not below 700, try 45. If at 45 you're below 700, then try 44 or 43. Target in on the exact year that will be over or less than 700 deer. We want to know the year that we take over that amount. And that way we know how many deer are actually there and that how many deer are left over. So, for 30 years, once again, we plug in 30 for x. That's where this 30 comes in. And we just plug it into our equation that we had for letter A. We plug that in on the calculator, we get the answer as 2,748 deer. Next, for letter B, again, we plug in 40 for x, and that'll give us 295 deer. So we know that the population dipped below 700 somewhere between 30 and 40 years. So at this point, you can start doing guess and check and plugging in 31, 32, 33 until we hit right below 700. Or you can use the table function here. So to find when it reaches 700 or fewer, use the table function on the calculator. We also must know that it must be between 30 and 40 years because, again, we can see that in our actual amounts of deer after 30 years and 40 years. So let's go ahead and enter that into our table function on the calculator right now. As I enter it in, 2,220,000 multiplied by 0.8 raised to the power of x. And then I go ahead and I hit my table button. So from here, we just start scrolling down. And we start scrolling down until we reach right below 700. So we know that's going to be a little bit after 30 years. Right now I'm around 20. All right. So looking at this, at year 36 we have 720 deer. At year 37, we are just below 700 deer. We're at 576 deer. There's 576 deer at the start of year 37. So that means that somewhere in year 36, we finally overtook that amount of 700 deer. So that's when they became extremely endangered. So again, we're just going to take that number. In 37 years, the population drops below 700. So we want to take it the year after. So if I see that we're at 720 deer at year 36, that means that the next year will be under 700. So we're going to count it as the whole year, the next year that it occurs. All right. Number 6. The population of Mountain Point can be modeled by the function f of x is equal to 852 times 1.05 raised to the power of x, where x is the number of years since 1992, the year that we opened up the school. What was the population of when Mountain Point opened in 1992? By what percent did the population increase by each year? And what is the population in 2018? So, for our initial population in 1992, that's just our a value. So if we look at our function, these are all written as a times b raised to the power of x. So our initial amount would be 852 students. That was our population in our opening year. For part B here, percent rate of change. Well, that's going to be dealing with our R variable. And again, we're not given R in our equation. We have B is equal to 1, and if we look at our B value, it's growth. So we have 1 plus R. Well, if our B value is 1.05, that's equal to 1 plus R. And then we can just solve for R. I subtract 1 from both sides. We're left with R is equal to 0.05. From there, we want it as a percent. So I move my decimal place 2 places to the right, giving us R is equal to 5%. And then again, this is growth. So this is a 5% growth. All right, and then lastly, the population in 2018. So from here, I'm not going to just plug in 2018 for X. That wouldn't make sense. That's going to give me an extremely large number. Instead, I'm going to take this number, 2018, and I'm going to subtract 1992 from it. That will give us how much time has passed between 1992 and 2018. So if we look at this, it says 26 years. So what I plug in for X is 26. So let's go ahead and do that. We have 852 times 1.05 raised to the 26th power. That will give us 3,029 students. Now I'm going to round to the nearest whole number because I can't have 0.5 of a student. So we just round to the nearest whole number. So 3,029 students after 26 years, which is quite an increase in the amount of students at the school. And then here's just all the work again. The population in 1992 is the initial amount of students. To find this, look for the A value. Again, A value is 852. For part B, we use R is equal to B minus 1. Sorry, this should be B is equal to R or 1 minus R. B is equal to, let me go ahead and get rid of this. B is equal to 1 plus R. And of course, if I simplified it, I would get the same equation here, but rather than memorizing a lot of equations, just remember B is equal to 1 plus or minus R. That'll be a lot easier for you. So we see that our growth is a 5% rate. Then lastly, the population in 2018, well again, 26 years have passed. So if we know 26 years have passed, that's what we plug in for our B value, that's what we plug in for our X value, and we're left with 3,029 students. All right. Moving on. This is section 13.2 on the test, so keep that in mind. This will be its own test section as well. It says, write a table and an equation for the graph function. Is it growth or decay? So if we look at this, as our X values are increasing, meaning that they're going to the right, what is happening to our Y values? Well, if we look at our Y values, as we move to the right, our Y values keep getting larger and larger on their own number line. They keep going upward. So they keep increasing as well. So if that's the case, this would be a growth function. So this is growth. This is what a growth function looks like for exponential equations. So that's how we know. Now from here, we have to fill in our table. If we don't fill in our table and write an equation, we won't get the full points. So looking at this with our table, my smallest X value as a point is at -1. It's my smallest X value. The Y value for that would be 1/2. And we'll be able to check this as we go because, again, this is exponential. We already know that to be true. So it should consist of exponential growth in the table as well. When our X value is 0, our Y value is 1. When X is 1, Y is 2. And when X is 2, Y is 4. Our last one is when X is 3, Y is 8. So when X is 3, Y is 8. Now, to make sure that this is exponential, we're going to check for a pattern in our Y column. If there's a pattern in our Y column with multiplication, then it's exponential. So, What do I need to multiply 1/2 by to get to 1? Well, the answer is 2. From 1 to 2, I need to multiply 1 by 2. To get from 2 to 4, I must multiply 2 by 2. And then to get from 4 to 8, I must multiply 4 by 2. So if it's a constant rate of multiplication, then we know that we have an exponential function. And that's why this table makes sense here. Now from here, we want to write an equation. We don't want to forget about our equation or else we won't get full points for this. So we can just write it out as y is equal to our a value. Well, our a value is our y-intercept here. It's that point where we cross the y-axis. If I look at my table, when x is 0, y is 1, so that would be my a value. So a is 1. Again, I'll just box it on the table as well. So a is 1. Our b value is what we're multiplying by each and every single time. Well, we're multiplying by 2 every time, so b is 2. And then we just raise it to the power of x. And there's our function. So make sure that you guys don't forget to write out your function in these, or else you will miss points, and just be very precise with it. I know that's kind of difficult to assume where this point is at. You could be like, oh, it's at 1/4, oh, it's at 1/2. Just make sure that it's consistent all the way through. Obviously, we can tell that that's halfway in between, but as you get closer and closer to the x-axis, it gets more difficult to tell. And then again, here's our work. Growth, and then a is 1. B is the number below divided by the number above. So if I take any point on here, say 8, and I divide it by the number right above it, 4, and this can only work in the y column here, that'll give me my b value as 2. If I take 4 and I divide it by the number right above it, 2, I'll end up with 2 once again. So you can always do this method right over here. B is equal to number below divided by number above to find out what your b value is. Lastly, we plug it in. F of x is equal to 1 times 2 raised to the power of x. All right. Write an equation for this function. Is it growth or decay? So looking at this, our a value, once again, our a value is when x is 0. So when x is 0, y is 32. So that's our a value. To find our b value, we do number below divided by number above. And of course, as we can see, as time is increasing, the car's value is decreasing. So this would be a decay function. So again, a is 32. B, we do number below divided by number above, and it doesn't matter which numbers you choose. So if I do 16.7 divided by the number right above it, 19.65, we get 0.85. In fact, if you continue doing that, you'll get 0.85 every single time if it is exponential. From here, we just plug it into our function. Y is equal to a times b raised to the power of x, and we get y or f of x, this could be a y if you'd really like to, is equal to 32, our a value, times our b value, 0.85, raised to our variable x. All right. That's it for 13.2. Moving on to our last section, 13.3, I can graph an exponential function from an equation. Now, in this section on the test, if it's an online test, you won't actually be able to graph these functions. So instead, you're going to be matching them and making sure that you have the right function. So make sure that you guys are checking your tables. Your tables will be your key to doing these easier. If your table doesn't match your graph, then obviously that's an incorrect answer. So just be wary of that. So, letter A. Complete the table to find the values of y equals 1/2 times 3 raised to the power of x. Now, I highly suggest that you use the table function on your calculator for this. This will make it very easy. All you gotta do is enter in this part of the function, and you'll be good to go. If you don't have access to a calculator, there's an app called Calculate, I believe 84 or 82. It's on the iOS store. I highly recommend using that app. Or just plug in the numbers and solve for them with a calculator. So just plug in for when x is 0 and x is 1 and x is 2 and so on. So for this, I'm going to have one negative number, and I'm just going to go up by ones for my x column. And again, it's totally up to you, but make sure that you guys use the table function on the calculator for this type of problem. So, starting at negative 2 actually, and then I go up by ones each time. Now if I plug negative 2 into the calculator, into this function for x, so I'm plugging negative 2 in for x, my y value will give me 0.56. And we're going to round it to 2 decimal places or the nearest hundredth. I plug negative 1 in for x, we get 0.17 for y. I plug 0 in for x, we should get our a value, 0.5 or 1/2. I plug 1 in for x, well 3 raised to the first power is 3. Cut 3 in half and you have 1.5. I plug 2 in for x, well 3 to the second power is 9. 9 cut in half is 4.5. So again, these are going to be fairly difficult to graph, but we do know how we can graph these numbers on a number line. We know where these numbers lie. So let's go ahead and do that. Again, that's all we got to do for that first one. Oops, sorry. So for letter B, we're going to graph the function y equals 1/2 times 1.45 raised to the power of x. So again, we start off with our t-table to make it very easy for us. We fill in our x values, and then we'll solve for our y values. And again, use the table function on this. The table function is key for you guys. So let's go ahead and do that. For our, there we go. For our starting x value, I'm going to start at negative 2 for x, and then I'm just going to go up by ones. So I go up by ones, makes it real simple for us. I don't need to jump numbers. I plug in negative 2 for x. We end up with 0.24 for y. Now if I want to graph that on my graph, from my x-axis I go to the left, negative 2, which is right here. This is negative 2. And then I go up 0.24. Now if I look at these spreads here, it's going up by 0.25 each time. So 0.24 is right below this first line here. It's very, very, very close to it, but it's right below it. The next point that we have is 0.34 when x is at negative 1. So again, we move to negative 1 on our x-axis. And I go up 0.34. Well, this is 0.25. This is 0.50. So 0.34 should be a little bit above that, somewhere in the middle there. And again, it doesn't need to be precise. It will be on the graphs that you're choosing from, but just keep that in mind. Our next point is 0.5. So when x is 0, y is 0.5, or our a value. So I don't move left or right at all on my x-axis because x is 0. I go up 0.5, and I make my point. When x is 1, y is 0.73. So I move over 1 on my x-axis, go up 0.73 on my y. Then lastly, when x is 2, y is 1.05. And I mark that last point, and all of a sudden I have this nice graph here. Now I know that this kind of looks like a linear graph. However, it is exponential, and it will exponentially increase as these numbers get larger and larger. Once I get to like 10, 12, 15, you're going to see this increase very, very quickly. All right. Number 2, a student analyzed this data showing the number of bacteria in a culture exposed to antibiotics over time. So to get started on this one, we have this whole table here, and this is our last one for the review. We see that our time is in minutes. So we have 10 minutes, 20 minutes, 30 minutes, 40 minutes, and then I added on to the table here. So it's very important that we realize that we should add on to this table. Now, this student, he stated that it was an exponential equation. He justified his answer by stating that it was exponential because both the x and y values decreased by a constant subtracted amount each time. Explain his mistake. So if I look at this, exponential increases or decreases, exponential functions in general, am I adding or subtracting to get to the next step in the table? That's the main thing that he was saying. We're subtracting by the same amount. Well, if we think about this, no. For exponential equations, we always multiply to get to the next section of the table. We never subtract, we never add, we don't even divide. We always multiply. Now, you may argue if I'm dividing, I'm still moving on to the next step of the table. However, that will not be useful for us to find our b value, though it's not necessarily incorrect to say so. So again, that is his mistake. He's saying that we're subtracting each amount. However, it is exponential, but it's not because we're subtracting by a constant amount, it's because we're multiplying by a constant amount. And multiplying is the key here. It's because we're multiplying every single time. Now, how many bacteria in the culture after an hour? Now, the hint here is 6 10-minute periods. So, if we think about this, there's 60 minutes in an hour, and that's why I extended my table a bit. So I need to get 50 and 60 here. So if we look at this, if I take a number below, divide by the number above, and this is just a table that's turned on its side, so this is my number below, 1800, divide by the number above, 5400, we realize that we're multiplying by 1/3 each time. Multiplying by 1/3. So 1800 multiplied by 1/3 will give me 600. 600 multiplied by 1/3, well, if I just divide 600 by 3, we get 200. So in 60 minutes, there is 200 bacteria remaining. All right, guys. That's it for the review. Please make sure that you guys study this up. Make sure that you guys ask any questions before the review date is finished up and the test date has arrived. If you ask me any questions after 9 a.m., I will not be answering any questions until the test is finished. I will answer your questions after the test. That way you can be prepared for a retake if needed. But keep that in mind, guys. If you don't ask the questions prior to the time that I lock it for the test, I won't answer them. Other than that, good luck, guys. I hope that you do well. If you need anything, please let me know. Stay safe. I'll talk to you guys soon. Take care.